In the last lesson, we looked at the basic elements of a circle. For our next lesson on circles, we will learn how to plot a circle on the coordinate plane. Circles can be plotted on the coordinate plane just like a line or a parabola that we've plotted in algebra. To see a circle plotted on a graph, we need an equation to map out our points. Let's assume we have a hypothetical circle with a radius of length r and a center at the hypothetical location hk on the graph. The equation of a circle with a radius of r and with a center at hk is the square of x minus h plus the square of y minus k equals r squared. With a keen eye, you might notice that this formula is the same as the distance formula between 2 points on the coordinate plane, which is d equals the square root of the square of x2 minus x1 plus the square of y2 minus y1. If we square both sides of the equal sign of the distance formula to remove the square root and then swap the left and right sides, the similarity between the two equations is revealed. Using the distance formula for the equation of a circle makes sense, because we are trying to plot every point that is some distance, which is in our case a radius of distance, away from a certain point, the center. However, using the variables from the equation of a circle will be more helpful in quickly seeing information about the center and radius of our circle. If you recall from our first lesson on circles, we discussed the word locus. We defined locus as a collection or set of points that meet some criteria. If we are to understand the equation of a circle, we must use a more mathematical definition of the word. A locus is the set or collection of points that satisfy an equation. Satisfying an equation is the process of calculating which values make an equation true. Much like how the only value that makes this equation true is the number 8, thus satisfying the equation. The value of 6 for x would make the equation false, and the equation would not be satisfied. The locus of points that make up a circle are the points that satisfy this equation. The square of x minus h plus the square of y minus k equals r squared. The criteria, per se, is that any coordinate, xy, on the graph must satisfy this equation if that point is, in fact, on the circle. For example, if we had a circle with a radius of 1 and a center located at the origin, 0, 0, then plugging in our values of 1 for r, 0 for h, and 0 for k, then our equation becomes the square of x minus 0 plus the square of y minus 0 equals 1 squared. Following the order of PEMDAS, x minus 0 is x, y minus 0 is y, and 1 squared is 1. Our equation is simplified to x squared plus y squared equals 1. Remember, I mentioned earlier that the locus that makes up our circle is the set of points that satisfy the equation of a circle, which in our case is currently x squared plus y squared equals 1, since our radius is 1 and our center is located at 0, 0. Obviously, if our circle has a radius of 1 and is located at the origin, then we should expect points 0, 1, 1, 0, 0, negative 1, and negative 1, 0 to be on our circle, since all of these points are a length of 1 unit away from the center. Plugging in these coordinates into our equation will demonstrate that these values do in fact satisfy the equation, proving that these points are on the circle. What about a point that is clearly too far away from the center to be on the circle? How about the point 2, 2? Well, plugging in 2 for x and 2 for y, we get 2 squared plus 2 squared equals 1. You could probably already see where this is going. 2 squared equals 4 in both instances, and 4 plus 4 equals 8. 8 is not equal to 1, however, and therefore 2, 2 does not satisfy this equation, and the point is not on the circle. Now the first 4 points we plotted are the easy ones, since all we did was plot a point a distance of 1 unit away from the top, bottom, left, and right of the center. To bring about the curve of the circle, we will need a few more points. Obviously, our circle will be bounded between negative 1 and 1 on the x-axis, so if we choose a point in between those, like let's say 1/2, we can solve for y and find our next points. Plugging in 1/2 for x, our equation is now the square of 1/2 plus y squared equals 1. 1/2 squared is 1/4. We will subtract 1/4 from both sides to isolate the y variable. Then we will take the square root of both sides to cancel the square above y. This simplifies to y equals the square root of 3 over 4. If you recall from algebra, there is a positive and negative solution to a square root. Typing the square root of 3 over 4 into your calculator will give you approximately 0.866. In reality, though, the two solutions are 0.866 and negative 0.866. This gives us 2 points to plot on our graph, the first being 1/2, 0.866, and 1/2, negative 0.866. Solving for y for the remaining points would be very tedious, which makes having a compass or a circle stencil very handy when sketching the rest of the graph. And voila! We have our circle with a radius of 1 and a center at 0, 0. For our next example, we will sketch a circle that is not on the origin. Here, we are given the equation of the circle. The square of x plus 4 plus the square of y plus 5 equals 9. How can we determine the radius and center with this information? Remember, our equation for a circle with a radius of r and a center at hk is the square of x minus h squared plus the square of y minus k squared equals r squared. Examine the right side of our equation. Only a 9 is present. The standard form of the equation has r squared on the right side. If 9 is currently in the position belonging to r squared, then we must solve for r like this to determine the radius. To cancel the square above r, we must take the square root of both sides of the equal sign. The square root of r squared is r, and the square root of 9 is 3. Our radius is equal to 3. Now for the center. The information regarding the center of the circle is located on the left side of the equal sign. Can you notice a difference between the left side of the equation we are given and the left side of the standard form? One has plus signs, while the other has minus signs within the parentheses. Under what circumstances would minus signs be changed to plus signs? One instance is the presence of double negatives. We must determine what value can be inserted for h and k to result in an x plus 4 and y plus 5. If we choose negative 4 for h and negative 5 for k and plug them into our standard form equation, the equation will look like this. Simplifying the double negatives will result in the square of x plus 4 plus the square of y plus 5. Therefore, the center of our circle must be located at negative 4, negative 5, since these are the only values that will render our equation the square of x plus 4 plus the square of x plus 5 equals 9. With a radius of 3, a center at negative 4, negative 5, we can now sketch our circle. 3 units above our center is the point negative 4, negative 2. 3 units below, negative 4, negative 8. 3 units to the left and right are negative 7, negative 5, and negative 1, negative 5, respectively. With these 4 points, using a compass or a stencil, a circle can be easily drawn through these points. We will end the lesson with a final tip on determining the center of the circle. If you are given an equation, like in the previous example, the square of x plus 4 plus the square of y plus 5 equals 9, and notice that the equation has plus signs in the parentheses, you must assume that the x and y coordinates of the center are negative. Again, in relation to the standard form of the equation, only double negatives will simplify the equation to have plus signs in the parentheses. Conversely, the square of x minus 3 plus the square of y minus 2 equals 25 has minus signs in the parentheses, like the standard form, and you would assume in this case that the center is located at a positive 3, positive 2. This assumption is correct, since dropping these coordinates into the standard form equation doesn't change the signs. Additionally, this is the only equation that correlates with the points of this particular circle. Now, if only one parenthesis had a plus sign, like these two examples, then whichever variable, h or k, is positive in the equation will be negative in terms of the location of the center, and vice versa. Hopefully this provides a guide to determining the correct location of the center of a circle when you're given an equation. Now that we have covered the definition of a circle, properties of a circle, and the equation of a circle, we will move forward in the next lessons to discover theorems regarding lines that have special relationships with circles.